You might think the ultimate speed limit of your computer is determined by its processor. In reality, it is actually bound by the speed of light and the physical distance inside the machine. Modern CPUs execute billions of cycles a second, but to actually do any of that work, they have to physically fetch instructions from the main memory, or RAM. Compared to the processor, RAM is agonizingly slow. The CPU ends up sitting idle, wasting cycles while it waits for electrons to travel across the motherboard. This hierarchy diagram shows the engineering fix. Storage is stacked like a pyramid, balancing speed, capacity, and distance. Topmost are registers. Below sits the cache, a high-speed memory pool next to the cores, preloading data so the CPU skips the slow trip to main memory. For moving large chunks of data, like loading a massive file from a hard drive, the architecture uses direct memory access, or DMA. This is a dedicated hardware bypass. It handles bulk data transfers in the background, completely freeing up the main processor to keep crunching numbers without interruption. Every modern computer operates as an elaborate logistics operation. The entire physical architecture is designed specifically to hide the slowness of the real world from the processor. Engineers manipulate time using pipelining, treating processing like an assembly line. The CPU breaks instructions into stages, executing them simultaneously. But this hits a limit, a pipeline hazard. If Step 3 needs Step 2's unfinished result, the assembly line halts. The system stalls. Notice the italicized stall blocks in this pipeline chart. Engineers map out these inevitable delays and build forwarding paths directly into the hardware. This reroutes data to exactly where it's needed, bypassing the wait to maintain the sequence of execution. We can push silicon to its absolute physical limits, overlapping processes and hiding memory delays, but eventually we run out of hardware tricks. That is exactly when we crash into an entirely different kind of boundary, the limits of a logical capacity. To solve problems, a computer must follow strict mathematical rules known as a formal language. The hardware is just the physical engine. The logic dictates what that engine is capable of understanding. The most basic logical model is the finite state machine. It is incredibly efficient at recognizing simple, regular patterns of data, moving from one strictly defined state to another based on the input it receives. Yet the finite state machine has a severe bottleneck. Its memory is strictly finite. It cannot count indefinitely, and it is mathematically incapable of processing deeply nested, complex information like an equation with multiple parentheses. To overcome this, computer science scales up the logic using context-free grammars. This is a much more powerful framework that gives machines the ability to handle nested structures and infinite patterns. This derivation example shows exactly how it works. A context-free grammar uses production rules to repeatedly replace a starting symbol with specific strings of variables and terminals. This substitution process creates infinitely generating structures, providing the exact mechanical foundation required to build modern programming languages. Look at this section on ambiguous sentences, showing two different leftmost derivations for the exact same input string. This introduces a new logical hurdle. When a grammar is ambiguous, it generates a structure that the machine can interpret in multiple, conflicting ways, causing the internal logic to break down. Even with advanced mathematics, controlling logic is difficult. It poses the ultimate question. Without physical speed limits and with infinite memory, is there a boundary to what it can solve? To answer that, we strip away all physical constraints and look at the ultimate mathematical abstraction, the Turing machine. It is a conceptual device with a read-write head moving methodically back and forth across an infinitely long ribbon of tape, with infinite time to work. Because it never runs out of memory and never overheats, the Turing machine represents the absolute theoretical ceiling of computation. If a Turing machine cannot compute something, no computer ever built will be able to either. For many tasks, the machine will process the input, eventually halt, and provide a definitive yes or no answer. We call these Turing-decidable problems. But there is a final, unbreakable wall. There are mathematical questions where even a perfect machine, possessing infinite time and space, will simply run forever, trapped in an endless loop without ever reaching a conclusion. We call these undecidable problems. The most famous of these is the halting problem, which asks if an algorithm can look at another program and determine whether it will eventually stop running. Alan Turing proved that no algorithm can solve every possible case of this. It remains computationally impossible. This proves that the universe contains questions that are mathematically unanswerable. It doesn't matter if we invent quantum computers or processors 1,000,000 times faster than today's hardware. No amount of computing power will ever resolve them. Computer science is a constant battle on two fronts. Engineers fight the physical constraints of the real world with clever architecture and hardware bypasses. Meanwhile, theorists navigate the inescapable boundaries of mathematics, mapping the very edges of what is known.